I want to go over the problem that's on your Newton's laws tutorial. It's number 9, where you're given the graph showing the force on a force plate while someone is jumping up and down. So I'll just sketch the graph here. And it's kind of hard to tell what the values are. So I've made it, this number is 686 newtons. And then it jumps up, down to 0, and then a sharp, short peak after that, and then back to the 686. So the first peak here, I think I had 1600 newtons, and the second peak, 2100 newtons. Okay, so what this graph shows, this is time. On this axis in seconds, and it tells you that the duration of this force occurs over a time of 0.25 seconds. Okay, so what this means is if you're standing on a scale, there are two forces on your body. One is the force of gravity, and that doesn't change whether you're jumping up and down, standing still, in the air. That never changes. But the force that the scale has to exert on you to keep you from falling through is the normal force. And that's what the scale reads. Okay, so the reading on the scale is the normal force. And that's what this graph is. This graph is the reading on the scale. Okay, so clearly it changes depending on how you're jumping around on that scale. Now, it goes through various stages of this jump. So the first stage here, A, you're just standing still. And if you're standing still, oops. So A is standing still. That means your acceleration is 0. That means your net force is 0. And the net force is always up minus down, so it's the normal force minus the force of gravity, and that's equal to m times a. So if you're standing still, the normal force equals your force of gravity. If you're pushing off to accelerate your body up, then the normal force is bigger than the force of gravity. If you're in the air, the scale reads nothing, so the normal force is 0. When you land back on the scale on the way down, a big force needs to stop your body, and that is the normal force. And so once again, the normal force is bigger than the force of gravity when you're landing. That's why that graph has all positive values. It's never negative values. So it's positive when you jump up. It's also positive when you land. Okay, so standing still, the reading on the scale, Fn, is equal to the 686, which must be the force of gravity. That's how you know what her mass is. So if that's the force of gravity, then the mass must be 686 divided by 9.8 newtons per kilogram. So her mass must be 60 kilograms. Okay, so you don't actually, sorry, that's 70 kilograms, darn. Hang on. 686 over 9.8 is 70, not 60. Okay, so you don't need to be told the mass because you can find that out from the reading on the scale when she's standing still. Okay, part B is when you're pushing off in order to accelerate your body up so that you can leave the ground. Okay, so this is the push off stage. And once again, F net is still always normal minus gravity. But now you do have an acceleration because you're accelerating your body up. So, and the reading on the scale, you just read it right off the graph. So Fn, according to that graph, is 1600 newtons. Okay, now I think I'll just, okay, we'll answer the questions in the order in which they're asked. So we're just trying to get the normal force for each section. So part C, when you're in the air, well, the reading on the scale is 0 because you're not on the scale. So the normal force is 0. Part D, when you're landing, a big force has to push up on your body to stop you, otherwise you go right through the floor. So when you're landing, once again, you read the value, the normal force right off that graph. And from the graph, Fn is 2100 newtons. So a bigger force than when you're taking off. And that's because you tend to land much more quickly and come to a stop more quickly than when you're pushing off to accelerate up. Okay, so that Fn, and that, once again, that's reading on the scale. And that is also on the graph. Okay, and then once again, when you stop and you're still, for part E, then the normal force is your weight again, 686 newtons. Okay, and you can see that from the graph. That's A, that's B. When you're pushing off, you have to push against the floor really hard. The floor pushes back. When you're in the air, the floor doesn't have to do anything, 0. As you come crashing back to the floor, and the floor needs to stop you from going through the floor, that's the biggest force, because that is quick. And then now you're standing still again, and you're right back to your normal weight of 686. Okay, so that's question 1, or A, and B. Okay, now we need the acceleration. So calculate the accelerations. Okay, for standing still, obviously the acceleration is 0, you're not moving. As you push off, the acceleration is the net force. So F net is Fn minus Fg. So the net force is 1600 newtons. That's how much the scale has to push. But then you've always got gravity pulling you back down. And so the net result is 914 newtons. And that leads to an acceleration, which is F net divided by your mass of 914 over 70 kilograms. And so you have an acceleration of 13 meters per second squared up. It's a positive number, so you're accelerating up. That's what gives you a velocity, so that when you leave the ground, you can keep going up. Okay, when you're in the air, your net force is just gravity. There is no normal force. So net force is 0 minus the force of gravity, because the normal is 0. And so this is equal to negative 686 newtons. Your acceleration is F net divided by m. It's negative 686. The force is down. That's why it's a negative. You divide by 70. And sure enough, you get negative 9.8, which we knew already. That's always your acceleration when you're in the air. Negative 9.8. You're accelerating down. That slows you down, stops you, turns you around, brings you back to Earth. Now, when you land, there's a very large upward force on you. So your net force, always Fn minus Fg, 2100 newtons, minus your weight, 686. So now your upward force to stop your body is 1414 newtons. So your acceleration, F over m, 1414 over 70 is 20.2. Now that's a positive acceleration, but that doesn't mean you're speeding up. It means you're slowing down in the negative direction. And the two negatives, slowing down and down direction, they combine to make it a positive acceleration. Okay, and E, you're standing still again. Standing still, and so once again your acceleration is 0. Okay, that's part C. Now we want to know some velocities. Now we have accelerations. Now we can go to kinematics and we can do some velocities. Oops. So part D to this question says, what was her velocity just as she left the floor on the way up? Okay, so this is the push-off stage. So what do we know about the push-off stage? Starts at rest. That's when you're in a crouch, ready to start pushing. We just worked out the acceleration because we have the normal force, so we worked out the acceleration while you're straightening your legs to push off. It's 13.1. We have the time from the graph. You push off for 0.25 seconds only, so it's a quick push off. And we want to know just what is your launch speed, or what is your final velocity after you push. Okay, so this is just straightforward kinematics. Vf is Vi plus At. 0 plus 13.1 times 0.25 seconds. And so you leave the ground with a speed of 3.28 meters per second up. Okay, and that would be your takeoff speed. Takeoff velocity. It's up. Okay, next question. Next question is, what was her velocity just before she hit the floor on the way back down? Well, anything that leaves the ground traveling up at 3.28 meters per second, neglecting any air resistance, will rise, stop, turn around, accelerate, and just before it hits the ground, it will be going exactly the same speed. This is V landing, but opposite direction. So the velocity is negative 3.28 meters per second. So as long as you're at the same elevation, so you start and land on level ground, your landing velocity will just be the negative of your takeoff velocity. Okay, F. How high did she jump? Well, we can use some kinematics here. How about we do, at the top here, we know the velocity is 0. Vf equals 0. So we can get delta y. Delta y would be the height of the jump. Okay, so once again, the kinematics for this is a very common kinematic equation that we use for these jumping questions. We have Vf squared is Vi squared plus 2a delta y. Remember, this is just free fall, so we know the acceleration is negative 9.8. And so the height of the jump would be Vf squared minus Vi squared over 2 times the acceleration. So at the top, velocity 0, the ground, 3.28 squared, acceleration while you're in the air, negative 9.8. And so height of the jump would be only 0.549 meters. Okay, not terrifically high, but nice jump. Okay, G. How long did the landing take as she brought herself to rest? Now we can see from the graph that it's pretty quick. The force is huge, and you're brought to rest in a very short amount of time. We want to know just what that time is. So remember, just before you hit the ground, so let's just make it a ball. So say you're here just before you hit the ground. You're going down at, this will be our initial velocity before we hit the ground, at negative 3.28 meters per second. And then let's say we squish down till we stop. Vf is 0. And it's not free fall. We've touched the ground now. There's a huge force up on us to stop us. And we know the acceleration during that process is the 20.2 meters per second squared. And what we want to know is how long does this take? So this is the unknown. Okay, and so the equation we want is Vf equals Vi plus At. And so T is Vf minus Vi over A. Vf is 0, you stop. Vi is negative 3.28. Notice those two negatives there. And then the acceleration is positive 20.2. And this gives a time, stopping time of only 0.16 seconds. So less than the 0.25 it took to push off. Okay, that's the end of that question.